All right, so now we'll start the lecture, and should see the whiteboard here. And again, as I said, the recording should only be of the whiteboard, not of the videos. So you can feel free to keep your cameras on. That'd be helpful. Yeah. So yeah, welcome back, everyone. And let's get right to it. That's the nice thing about this year-long sequence is we can sort of jump right into things. But yeah, interrupt me as usual if you have questions or comments. Yeah, that should do it. Oh, by the way, on the syllabus, there's a kind of tentative schedule of topics. You can look at that as well. But the first thing on our agenda, so to speak, is the hydrogen atom. And it's not really. So what we're trying to understand is if we have a proton sitting there and an electron, we're just trying to understand the energy levels of the electron in the Coulomb potential, because there will be a Coulomb interaction between these two oppositely charged particles, and we're just trying to understand the energy levels of the electron. That's what we're going to be doing. That's our first application. And as usual, as a review of the first semester, the only relevant parts you have to remember is that you have quantum mechanical systems that are described by complex vectors that live in a Hilbert space. So and we know that the time evolution of the complex vector is given by the Schrodinger equation. And H here is our friend, the energy operator, the Hamiltonian. It's Hermitian. It's got real eigenvalues, which are the energy levels. And, we spend a lot of our time trying to understand the spectrum of this guy, the energy levels of the system. So we find the eigenvalues and eigenvectors. And, knowing those, you can, of course, decompose psi into a basis of the eigenvectors. And then it's really easy to solve this equation because each component of your expansion would just pick up a phase based on the eigenvalue, the energy level. And so that's what we're going to do with hydrogen, is figure that out, figure out how, figure out what the energy eigenstates are and solve essentially the Schrodinger equation, or at least find the eigenvalues and eigenvectors for the energy operator associated with the Coulomb interaction. Yeah, and of course, remember when we talk about physical properties, it's always, for instance, if we calculate, say, the expectation value of some observable, it's written in terms of the inner product between the system's state vector and, of course, the observable, which is an operator, which acts on the vectors. So we have those expectation values. This would be the expectation value of observing A, given that the system is in state psi, which is what you would get if you measure A over and over again. This would be the average value. And we, of course, also have probabilities, say, observing a system in some other state B. We would take the inner product between psi and the complex vector associated with state B, and take its square. So that's really it. I mean, really, all of quantum mechanics boils down to these basic things, and everything else is just, it's kind of details and complications. But let's try with the hydrogen atom. Let's try to find the eigenvalues and eigenvectors of H, and see how it goes. So to begin, let's remember, so you see this, if we think about the proton as sort of, it's a large, right? It's much more massive than the electron. So it's sort of like a stationary object, and the electron kind of whizzes around it. And of course it whizzes around in 3D. So one of the other examples that we looked at that's sort of like this was the rigid rotor. And the rigid rotor, it had two masses attached with a little bar, some distance d naught away, and this thing sort of spins around in 3D. And that had an energy which was given by, of course, it's just a kinetic energy. There's no potential. So the kinetic energy, it's due to the rotational motion. It's 1/2, and then the equivalent of mv squared, right? But in for rotational motion, so that's the moment of inertia times the angular velocity squared. So it's like 1/2 mv squared for rotations. You can rewrite that in terms of the angular momentum, which is the rotational version of momentum, of course. So instead of p squared over 2m, you have, L squared over 2I. It's, again, it's just a rotational version. It's things you should remember from classical mechanics. It's just that we looked at this particular energy operator. You see, it's just proportional to angular momentum squared, and we know what the eigenstates are, right? We spent a lot of time last semester talking about these eigenstates of angular momentum. They were given by two quantum numbers. The first one labels the eigenvalue of L squared, which was h bar squared L plus 1. And the second one is related to the eigenvalue of the z component of angular momentum, which is h bar m. And we know that, L ranges from 0, 1, 2, and so on, and m ranges from -L all the way up to +L. So we know what everything is, right? These are the eigenvalues of this operator right here. So those will tell you the energy levels of a rotating thing, right? And what's the degeneracy? Each of these energy levels will have this many m's it could be in. So that's 2L plus 1 different states corresponding to the same eigenvalue of L squared. So there's for this operator, there's a 2L plus 1 degeneracy for each energy eigenstate, right? So so for each energy, sorry, for each eigenvalue of the for each energy level, there's a 2L plus 1 degeneracy, and you can so again, the energy levels are labeled by this L, and it's just h bar squared L plus 1 over 2I. Those are the energy levels, and these are the energy eigenstates, and again, there's this degeneracy. What else? We also know what the wave functions look like. We can write out what the sort of angular distribution is, right, this guy. If you imagine this thing in sort of spherical coordinates describing its orientation, then in position space, the wave functions are just the spherical harmonics. These are the YLMs. So that's what the eigenstates are in position coordinates. So this is all helpful. Why? Because it'll help us understand the hydrogen atom, which again, it's also has this element of rotations, right? There's a sort of 3D space in which the electron whizzes around. So we'll have a radial coordinate, right? Describing the distance away from the proton, but there's also the theta and phi coordinates, which give us the rotations. And so this is just a reminder of last semester where we did, eigenstates of angular momentum. This is what we found. We talked about spherical harmonics for some time. So we'll need that. We'll be using that again for the hydrogen atom. Any questions so far? Comments? Yeah, sort of easing back into it, but yeah, interrupt me whenever. So yeah, so what about the hydrogen atom? Or it's really an electron, interacting with a proton. So what about this? So what the hydrogen? What's the energy operator? Well, there's of course a kinetic energy for the electron. That's just our p squared over 2m, and there's a potential. And for now, we're just gonna, it's the Coulomb potential, of course, but we'll just think about generally radial potentials, right? Some kind of potential that just depends on the distance between your object of interest, and just in this case, the electron here of mass m, right? And there's some potential which describes its interaction with the proton, or it might be some other object. I don't know. It's just some kind of position-dependent potential here that only depends on the distance between your object of interest and then some center of the potential. Could be a Coulomb potential, as we'll study, but it's arbitrary radial potential. So what is this thing? Remember that it's convenient to think about this operator in position representation. And if you recall, minus p squared over h bar squared is going to be minus, and the p in position space is minus I times h bar times the gradient. So this whole thing is like this. The h bars cancel here, so p squared over h bar squared with a minus sign is just the Laplacian. It's the gradient dotted into itself. It's the Laplacian operator. That's how the momentum acts on spatial wave functions. And if you think about 3D things, right? You can write the Laplacian in spherical coordinates, and you can look that up in Jackson or whatever. It's probably seen it. You obviously saw it at some point last semester, but you can just look this up in spherical coordinates. It's 1 over r dr squared r. And remember, these are operators, so this is like acting on a function. This thing acts on functions of spherical coordinates, right? Like this. So when I write something like this, remember it's r multiplied by f, and then you take r multiplied by f and you act with 2 derivatives on it, right? And then you divide by r. So it's just nice shorthand. It's a derivative operator. And then we have 1 over r squared And we have 1 over sine theta d theta sine theta d theta plus 1 over sine squared theta d phi squared. So again, the way it works is these are up. So first you take a derivative with respect to theta, multiply by sine theta. You take all of that and differentiate it with respect to theta, and then you divide by sine theta. Here you take 2 derivatives with respect to phi and divide by sine squared theta. And what this is, it's nothing but 1 over r dr squared r. There's just a radial piece, and the rest of this is minus L squared over r squared. It's the operator here, if you go back and look at your notes from the first semester on angular momentum, here this is just the the position space representation of the L squared operator. So the kinetic energy is composed for in spherical coordinates is composed of a radial piece and an angular piece, and unsurprisingly, the angular piece is just proportional to the angular momentum squared. And that's the kinetic energy, and then the potential is just a radial piece. So that's very convenient because we know then, right, that our wave functions, psi, will at the very least be labeled by L and M, right? Because we can diagonalize L squared. We know how to do it. We can find its eigenvalues and eigenvectors. We already know what they are, right, from the rigid rotor. They're the spherical harmonics. So that's very nice. So the rest of the whole goal here is just to solve now the radial piece. You can take care of the angular part of finding the eigenvectors by just using the spherical harmonics. And so all that's left is finding the radial part. And that's the hard part, and that's what we'll do for the hydrogen, but for the Coulomb potential. And so what's the idea here? Your wave functions are just going to have the form, they're going to be YLMs, and that'll take care of the angular part. And then there's a radial piece, and we can already say something about it. So it'll be some function u, and it's convenient to divide by little r. We'll see why. You don't have to, but it's convenient to define this function u. So this is the form of our wave functions of our eigenvectors of h. There's the angular part and then a radial part, which we'll find. So who can say, can this depend on, what can you depend on? Can it depend on, say, little m? You want to have thoughts about that? Can it depend on little m? Yes or no? All right, let's take a little vote. You guys can raise your hands. Raise your hands if you think it can depend on little m. All right. Yeah, we got some. Oh, it even tells me now how many. Okay. I got a couple of people. All right, who thinks that it can't depend on m? Let's see. Oh, there's a few more. We got 5 now. All right. Yeah, well, the majority was right. It was 5 to 4. It cannot depend on m. And it can't depend on m because remember what m is. M is the eigenvalue associated with LZ. It's a particular direction. And the U part is the wave function associated with the radial piece. But the radial piece is spherically symmetric. It doesn't know about the Z direction, right? So it can't depend on M. But how about L? Who thinks that it can depend on L? All right, yeah. All right, I think we got up to 4. All right, so 4 for L dependence. How about no L dependence? Doesn't depend on either L or M. Any takers for that? All right, I think we have. I think the L dependence won by like a couple of people. So indeed, you can depend on L. Why can it depend on L? Because L is the eigenvalue associated with L squared. L squared is spherically symmetric, right? It's a scalar. It's doesn't depend on, it's the magnitude of a vector, right? The magnitude of a vector doesn't care about which way the vector is pointing. It's, so indeed, this can depend on L. All right, so good. So this is hopefully, this is also a bit of a review of symmetries, right? You can use symmetries, in this case, rotational symmetry, to, make some pretty strong constraints on the form of the wave function. We know the wave function for this kind of Hamiltonian will just have a spherical harmonic out in front, and it'll have a radial piece, and the radial piece can only depend on this L. It can only depend on this L quantum number, because that's the only piece that remains invariant under rotations. And the radial thing, it just depends on little r, right? The distance between the two things. It doesn't depend on the orientation. So all the orientational stuff is captured by the spherical harmonic. Okay, so now what we do is we just take H and we act with it on psi LM, right? So what do we get? We get from this piece, we get minus 1 over 2m. I suppose I can put in, no, for the most part, we're going to set h bar equal to 1, but you could put it in if you want. I don't really like to. You could put an h bar squared here instead of this 1, but I'll just leave it like that. And you have 1 over r, and you have dr squared acting on u. See, this is why this is nice. The u over r is nice, because this operator here, the first thing it does is multiplies by r. So that cancels this r right here in the denominator. So that gives us a nice term for this one. And I'm going to pull the spherical harmonic out, of course. Then you have this L squared over R squared business, right? But we know the eigenvalues of L squared, that's just L plus 1. So there's an L plus 1 over 2m. That just comes from the p squared over 2m. And then there's a little r squared here. Remember, this thing we said is minus p squared, so plus p squared, it would be plus L squared over r squared. And again, h bar is 1, so you just get L plus 1 over 2mr squared. Then you get your potential. which again depends on only the radial coordinate. Now this is no longer an operator, but the actual radial coordinate, because we're in the position representation, so we can replace the position operator with the coordinate. And that's all acting on UL over R. What else do we have? Then we have the spherical harmonic, which just comes out. And that's all equal to, we're supposed to find the energy eigenvalues. So we see that there's this L in here. So that means the energies can in principle depend on L. And then phi is just UL over R, YLM theta phi, right? And that's very nice because the YLMs cancel. And you're left with just an equation for U, right? And moreover, this cancels here, right? This R cancels everything. Now reads very nicely. Just get an ordinary differential equation for the U's. Just get two derivatives with respect to R. You have the centrifugal term, which depends on L. This is the important equation to solve, right? For any kind of spherically symmetric potential. You see there will be a separate wave function for each value of L. And for each value of L, these are also sometimes called partial waves. And each value of L often has a special name. So again, L is 0, 1, 2, 3. These are often called partial waves. Each one is a partial wave. I'm actually not too sure what the etymology is of that. I think it makes more sense in the scattering context why it's called this. But in any case, for each L, you have to solve a separate 1D Schrodinger equation, right? This is nothing but like a 1D Schrodinger equation with a kind of modified potential that gets modified by a piece that came from the rotational kinetic energy. This guy, it's the centrifugal part. And what does it do? You see a larger L, this part starts to dominate. It has a 1 over R squared shape. So it looks like, this, right? 1 over R squared. And what it means is for larger R, right, there's going to be a potential barrier for around R equals 0. It means, it makes sense, right? If you have more angular momentum, thing is whizzing around faster and faster, then it'll tend to be pushed away from the origin, right? Whatever your object is. So for larger L, you get an effective contribution to the potential that pushes you away from the origin. You get sort of, as you whip around, you get pushed out. That's kind of the effect of this term. And it's called a centrifugal barrier. It's called a barrier because, of course, it diverges as R goes to 0. And so it prevents any kind of, it suppresses the wave function near the origin. So it acts like a potential barrier. Remember potential barriers that we studied. That's what it is. It's a potential barrier at the origin, right? Because that piece of the potential blows up there. So yeah, and so this is what we'll look at for hydrogen. Of course, we just have to replace this V with a Coulomb potential. And we'll go from there. But this is another good place to pause and see if there's any questions. Okay. So this is not the only thing that matters, right? So this is the time-independent Schrodinger equation. Remember that if we're looking for proper energy eigenstates, right, we have to combine this equation with a normalization condition that if you integrate over all coordinates, if you integrate, the psi lm, r theta phi, that should give us 1. There's a normalization condition. And this condition, if you recall, what it typically does, so this is for bound states, right? Wave functions have to be normalized. For bound states, this equation combined with this, and again, remember that the psi's are given in terms of the u's like this. This extra condition that the wave function is normalized gives you this quantizes your energy levels. It introduces another quantum number which labels the energy levels. So what we'll then have is that for any given value of L, right, we in principle could have a whole set of for any fixed L, the normalization condition for that fixed L will quantize the possible values of E. So this E in principle can have another quantum number associated with just solving these two things simultaneously, the Schrodinger equation combined with the normalization condition. So that's the general scheme of things. And now what we're going to try to do is try to understand this this equation in more detail. And how we're going to do that is we're going to try to see what happens to this equation in the limits of large and small r. So we know this part blows up near the origin, so something interesting must happen there, right? And we'll also try to understand what happens at large r. And by studying those two limits in combination with the fact that the wave function has to be normalized, we'll be able to kind of guess at a good solution for u. We'll be able to solve this equation that way by looking at what happens at small r and large r. It's a very common theme in theoretical physics in general, is that by looking at different limits of this equation, that'll help you solve the equation, for any r, just in general. So that's the kind of that's the idea. So the first thing to do is to see what happens at small r. And at small r, well, if u is like a normal function, right, then we would expect to be able to Taylor series expand it, right? So any function of r here, if we expand it around, zero, for small r, we would find some coefficient, some initial Taylor series term, or it would be some power of r here, right? It could be alpha could be 0, like it could approach a constant. We'll see that that's not actually possible, because that'll lead to issues here. If u approaches a constant, then you'll have a problem with this centrifugal part. It'll blow up, and that'll be a problem. But this is what we'll do. We'll take this as our kind of, so let's just say that at small r, u looks like, some constant a times r raised to some power alpha. And we can substitute that into the equation and see what happens. Well, first you take two derivatives, so you get minus big A over 2m. You get alpha minus 1, that's from the two derivatives, and then you get r to the alpha minus 2. Then you get the L plus 1 piece over 2m, and here you get r to the alpha minus 2 because it's divided by r squared. So that's alpha minus 2. Then you have the potential term. But if you think about the potential term, well, that should just be like whatever, times a, of course. That should just be whatever v is at 0, and if it's suitably regular, if it doesn't blow up at the origin, well, then you would get something like this, right? And on the other side, of course, you just get e a r alpha. Now, if you think about this, what happens is you send r to 0. These parts, right, will be much smaller than these guys, right? Because this thing has alpha minus 2. It's divided by r squared relative to these terms. So as r goes to 0, these terms will be negligible compared to these guys. So as r goes to 0, these two terms have to cancel each other out, so that these guys have to add up to 0, because these terms don't contribute. So they'll be much smaller than these guys, which are will be much larger. So what does that mean? If that's equal to 0, of course, what it means is that alpha times alpha minus 1 has to be equal to L plus 1, right? That's the only way these two terms can cancel each other. And that's an equation for alpha. So it means alpha is either minus L or it's L plus 1. And if we look at this guy, we can think about what that means. The minus L solution, right, would give us a u that looks like a r to the power minus L. That's not a very good solution because it blows up at the origin, right? And if it blows up at the origin, then you'll have a problem when you're doing this integral. So this is not good. This option is not good for bound states. Why? Because the bound states have to be square normalizable. If you start trying to integrate, r to the minus L squared, you run into issues. It blows up at the origin. So that's not good. This guy is okay. It's okay because it doesn't blow up at the origin. It just goes to 0 there at the origin. So that's okay. So we conclude from this that UL of R for small r, as r goes to 0, has to have the form, right, a r to the L plus 1. So that's pretty powerful because we'll be able to constrain the form of our solution by ensuring that when you take the form of the solution for small r, that the first term in the Taylor series expansion is L plus 1. And we got that just straight from the Schrodinger equation in the centrifugal barrier part. So that's pretty cool. So, okay. If we deal with scattering states, which don't have to be normalizable, things are a little bit different, and we could have this other solution here, and we'll see this later. we'll do this later. Later, we'll look at scattering solutions. And in that case, what the solution looks like as R goes off to infinity, it will look like the following. Your wave functions will be labeled by momentum. Again, there's no quantization of the energy levels now because we don't have that normalization condition for scattering states. We can have an arbitrary kinetic energy. And so the scattering states are labeled by their kinetic energy, which is continuous. And the general form of it, as we'll see, there will be a plane wave part, which is kind of incoming wave. And then there'll be a scattered portion with an angular component and an outgoing spherical wave. These are, looks like that. And we'll see that later. But for now, we'll not. For now, we'll just look at the bound states ones. And the bound states in red here, we argued that you can only have U go as R to the L. You won't get any of this kind of 1 over R business that you get for scattering. So the scattering is for later, but something to keep in mind. So for bound states, then we know that as R goes to 0, it has to have this form. It has to vanish as R goes to 0. So remember, L is 0, 1, 2, 3, and so on. Okay, so let's do the bound states of a particular example now. Let's do the hydrogen atom, which is the Coulomb potential, which remember is minus E squared over R. That's the potential. This E is not quite the charge. It depends on which kind of systems of units you use, but it's the electronic charge squared over 4 pi epsilon naught R. It's just the Coulomb potential. So let's just substitute that in, right, and see what we get. See, the Coulomb potential is a little bit trickier, right? It's there's a 1 over R there, and so the potential does blow up at the origin, and we might wonder, uh-oh, maybe that's not good in terms of this guy. But it's okay because a 1 over R would just give us an R to the alpha minus 1. And alpha minus 1 is going to be much smaller than alpha minus 2 as R goes to 0. So it's still true that the U's have to vanish according to this power law. Because we can still neglect both of these guys, even if, even if near the origin V vanishes like, or blows up like 1 over R, it's okay. These still dominate. Okay, so what's our differential equation? It's minus 1 over 2m. Let me just put in the derivatives now here. Got the centrifugal part, 2m r squared, and then we got a minus E squared over R. And we're looking for bound states, so they might be labeled with their own quantum number for each fixed L. And they might have, for each fixed L, it might have, a set of possible energy eigenstates. And that's the differential equation we're trying to solve. And when you see a differential equation like this, it's always convenient to get rid of all the constants. You want to get rid of all of the m's and E squareds running around. And if you recall, what we did in the first semester at the very beginning of class is we looked at atomic units. We looked at the Bohr radius and the Rydberg energy and so on. And those are exactly the right combinations of constants to use in order to rescale stuff. So you want to, what do you want to do? You want to introduce a new coordinate, which is little r divided by the Bohr radius. And the Bohr radius in terms of these coefficients m and E squared, it's just 1 over me squared. So this is me squared r. And, it should make sense, right? We want to replace R with something that'll cancel, that'll cancel these E squareds and M's. And the natural length that you can generate using M and E squared is just 1 over ME squared. And so this is kind of the natural dimensionless coordinate that you can define. And the other thing that you want to do is define a new energy, a rescaled energy. And we know that, what do we know? We know that this potential here is negative. So if we look at it, this potential will be a combination of kind of this guy and the centrifugal barrier, which sort of looks like this. So this is the Coulomb part, and this is the barrier. And together, when you add them together, they'll produce something that looks like this, right? Some kind of potential. This is this whole thing right here. And the point is, the bound states will all live down here, right? They'll all live kind of below 0. So the energies we get are going to be negative, right? Just from the shape of the potential, you can sort of just plot this, right? At large R, this thing will dominate because 1 over R squared falls off faster than 1 over R. So at large R, it will look like 1 over R, negative 1 over R. So that'll be down here. So all the bound states just have negative energies. So it's convenient to define a rescaled energy, which is minus this guy, right? Divided by what? Well, the characteristic energy that you can construct using these units, the ME squareds. And what that is just the characteristic Coulomb energy of an electron that's exactly 1 Bohr radius away. Or I guess it's more convenient to do 2 Bohr radius to make the factors of 2 a little bit nicer. But it doesn't, the factor of 2 is not really so important. The point is you divide by the Rydberg energy, which we looked at before too. And what that Rydberg energy was in terms of these E squareds and M's is just E squared divided by 2 A naught, which is the Bohr radius. And so you can rescale in this way. And it's very convenient because then all the E squareds and M's go away. And so by changing variables, what you'll find is a much nicer equation because no longer has E's and M's running around. And you'll practice doing this for another kind of potential on your homework. So you define a new wave function that's just, that's the old wave function, right? But now instead of R, it's A naught times, you replace R with A naught times X, right? Because R is equal to A naught times X. And if you do that replacement and you write down the differential equation for the V, what you do is you just get 2 derivatives with respect to X. You can use chain rule, right, to convert from R to X. You get L plus 1 over X squared. Again, the R squared gets replaced by A naught squared, X squared, and then there'll be an overall constant that just comes out and gets divided on both sides of the equation. You'll practice this on the homework, so it's okay. You can check this. It's just some algebra that it's just changing variables from R to X and from E to this epsilon. And what you get here is something that just has numbers in it. It's a very powerful, if you talk to like a applied mathematician or, someone who like solves these kinds of problems for a living, they'll always tell you that, the first thing you want to do is get rid of as many units as possible. Get rid of as many dimensionful things as you can by appropriately rescaling your positions and your energies, and sometimes your time if you have a time variable. Here we just have an energy and a position, so we rescale those two things to get rid of all the units, and we're left with a completely unitless equation, which is just a mathematics problem now that you can solve, and you have to worry about, the mass and the electron charge and so on. And this becomes minus epsilon NL, V NLX. And that's the equation you get. You see now there's no E squareds, no M's. You just get like X's, right? You get some epsilon, which is a dimensionless number, and you get L, which is 0, 1, 2, 3, 4, 5. Okay. And now instead of looking for negative energies, since we defined this epsilon with a minus sign, we're going to look for positive epsilons. So we'll have this condition as well. So this is the mathematics problem that we're trying to solve. Any questions about that? Okay. So far, so good. And now we know a little bit about what happens for small x, because we saw that the u's have to go like r to the l plus 1. So the v's have to go as x to the l plus 1 for small x. But what about large x? We can also say something about large x. At large x, well, we would hope that these terms, since they're divided by x, are negligible, right? And so you're left with this guy balancing this guy. And that's a differential equation. So what kind of solutions does it have? If you just throw out these terms, what's going to be a solution for V in that case?
Throw out which terms?
Sorry, say again?
You said throw out which terms?
So for large x, we can throw out these guys, right? These guys are small as x goes to infinity, right? Because they're divided by x. So if we toss those out, what kind of solutions do we get for V?
Exponential.
Yeah, exactly. We just get our usual friend, this differential equation that, this kind of thing, right? Two derivatives, you get back the function itself. So the solutions are proportional to e to the plus or minus square root of alpha. Again, this is positive here. The epsilons are positive, square root of alpha. So you have to worry about imaginary numbers or something. It's just these guys, right? That's the differential equation you get. It's exponentials, absolutely right. And so that means that for large x, right, we should, for large x, as x goes to infinity, this guy should be proportional to e to the minus alpha x, where alpha is square root of epsilon and L. And why do we throw out the plus? Because that's bad. Because if you have exponentially growing solutions, then you won't be able to satisfy our bound state condition, it'll be blowing up. That's not good. You can't normalize something that blows up like that. So V for large x has to be exponential. So we're going to combine these two ideas that you have this. You combine that with the idea that at small x or small r, proportional, of course, so you have that. These are the two kind of constraints for small x or r and for large x. And so that leads us to positing a solution for v and L of x. What's it going to be? Well, it's going to have an exponential part minus alpha x. And it's going to have another function of x. Sorry, I'll get rid of this other thing. It's a little bit confusing. It's going to have some function of x. And the function of x, well, we know that this function of x, it better have, if we're going to expand it and say a power series, it better have the following form, right? If I sum and its coefficients, ak, the first term in its Taylor series better be L plus k, right? With k starting at 1. Because the smallest term in the Taylor series has to be to the power L plus 1. We know that from the rainbow thing, right? The thing. This has to start with L plus 1. The exponential, of course, at 0 is just a constant. This is a constant. So this has to tell you the thing, the Taylor series of f is what's responsible for ensuring that v vanishes appropriately as x goes to 0 with power L plus 1 at least. And then it's a Taylor series, so you can have higher powers after that. L plus 1, L plus 2, those are all okay. Great. So now it seems a bit tedious, but this is really how we're going to do this. You have this as the form of your solution, right? You have the exponential part, and then you have the Taylor series. This is the form of your solution. And we know what alpha is. This is the square root of these guys. So alpha is square root of these guys. And you have these coefficients. These are the things that you want to determine. That's what will determine your solution. But all of the dependence on x is already known. We know it. We can try this as a solution in this differential equation. So that's what we'll do. So let me just begin there. The first thing to do, of course, is we won't put in the Taylor series quite yet. We'll just put in this part with the f. Well, you take this and stick it into this differential equation here. And that's going to look ugly, and you might say, well, we've done nothing to improve on our situation at all, but we'll see that it is actually an improvement. So what happens? You have to use the chain rule. You got first two derivatives with respect on the f. The prime just means the derivative with respect to x. It's just df dx. Two primes is two derivatives. Then you have the cross term where the derivative hits the exponential and the f. So you get a plus 2 alpha e to the minus alpha x f prime. You gotta do the two derivatives on this guy, which will bring down two factors of alpha. So it's minus alpha squared e to the minus alpha x f. This is just plugging this in and taking two derivatives, right? Derivative hits this guy twice, that gives us this term, hits this guy twice, that gives us this term. The derivative hits both, and there's two terms like that, so that's the cross terms. What else we got? We got the L plus 1 part over x squared e to the minus alpha x f. we've got the minus 2e to the minus alpha x f over x. And then we have the other side of the equation, which is just minus, this is alpha squared now, because alpha squared is epsilon and L, e to the minus alpha x f. Doesn't seem like we did anything to help our situation, but we did in fact, because now this gives us an equation for f. And I'm out of time here, but so obviously the exponential pieces all cancel. And you get this equation for f. And now we're going to stick in this Taylor series for f and see that we get a set of equations for the coefficients of that Taylor series expansion of the power series. And we'll be able to solve it and get the energy levels and solve the hydrogen atom. So solve for, the energy levels of an electron in the Coulomb potential. And you'll do something like this for another kind of potential on your homework, but the steps will be the same, except, it's a different potential. So a little bit different, but we'll start here next time. This is sort of a natural place to stop. We'll solve this equation, stick in the Taylor series and so on. All right, and that's kind of it for today. I was starting with a lot of nice math, but that's what happens when you do applications. It just turns into a very long and elaborate process of doing something that is simple to state, which is just find the eigenvalues and eigenvectors of your Hamiltonian, which I can write down very simply just like this. But of course, when you actually try to do an example, it always becomes a bit of a mess. But keep in mind, we're not doing anything complicated. We're just trying to solve for the eigen functions and eigenvalues of this operator. That's it. But when you're actually solving the associated differential equation, there's all sorts of mathematical tricks. And that's a lot of this class will just be like that, just studying various tricks for solving particular problems. This trick is quite general. It can let you solve all kinds of things, not just the Coulomb potential, but you'll see on the homework other stuff too. All right, any other questions, comments? All right, well, that was good. So yeah, good to see everyone. Let me stop the recording.